Hello again. In this video, we're going to talk about some of the problems that involve gas laws. We're going to focus on two problems, page 220 in your textbooks, number 94, and number 99 on page 221. All right, so 94, healthy male has lungs with a volume of 6 liters that fill with 0.28 mole of air when he inhales. After he exhales, the number of moles of air in his lungs decrease to 0.20 mole. What is the volume of air his lungs after he exhales, assuming constant temperature and pressure? All right, so this number 94, let's take stock of what we've been given. We have a volume, an initial volume of 6 liters. Okay, and let me take a look here, 6.0 liters, so this is going to be 2 sig figs. All right, and he breathes in 0.28 moles of air. All right, when he exhales, we don't know what the volume is. That's what we're looking for, but we're told remaining there is 0.20 moles of gas. And we're told that temperature and pressure are constant. All right, well, our combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. Well, since temperature and pressure are constant, we can get rid of them. And that leaves us with V1 over N1, initial volume over initial moles, equals ending volume with ending moles. Okay, so let's just plug in what we have. We have V1 at 6.0 liters. We have V2, we don't know. We have N1 at 0.28 mole, and we have N2 at 0.20 mole. Let me scroll this down so when we continue the calculation we can actually see what's going on there. So rearranging this algebraically to get V2 by itself, we just need to multiply both sides by 0.20 moles. So this becomes 6.0 liters times 0.20 moles all over 0.28 moles. Moles on top, moles on the bottom, they cancel. We do this math. V2 is going to equal 4.2857 dot 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 dot. All right, well, let's take a look. 2 sig figs, 2 sig figs, 2 sig figs. Well, we're going to have 2 sig figs. This is division and multiplication, and 2 sig figs will round us to 4.3 liters. So that's the answer to our question using the combined gas law. All right, let's take a look here. We wanted to look at also on page 221, number 99. So let me scroll down here. Number 99, and this one's going to use the ideal gas law. It reads a sample of oxygen that contains 7.00 times 10 to the minus 3 moles has a pressure of 712 millimeters of mercury and a volume of 205 milliliters. What's the temperature of the sample? All right, well, let's write down what we know. We know that we have a pressure of 712 millimeters mercury. We know we have moles, 7.00, I think it's 3 sig figs, yes it is, times 10 to the minus 3 moles. Okay, and we are looking for temperature. And the last bit of information I think we have is volume equals 205 milliliters. All right, well, looking for T, V, and P. We don't have a case 1, case 2. We just have one single case. So that is a dead giveaway for the ideal gas law. PV equals nRT. If you have a case 1 and a case 2, a before and after, yes, the combined gas law is what you're looking for. But if we have a single case, we're not changing anything, it's the ideal gas law. So now, the only thing in our particular formula here is this R. Remember, R is a gas constant. 0.0821 atmospheres times liters over mole times Kelvin. That's what I memorized back when I was in high school 30 years ago. And there are other permutations of this gas constant depending on your units, but I always know it in atmospheres, liter, mole, Kelvin. So that means we're going to need our pressure in atmospheres, we're going to need our volume in liters, and we're going to need our moles in moles, and our temperature is going to need to be an absolute temperature scale of Kelvin. All right, well, we need to rearrange some things here. Pressure we have in millimeters of mercury, we need it to get in an atmosphere. We know that a normal atmosphere is 760 millimeters of mercury. So our corrected pressure, 712 millimeters of mercury over 760 millimeters of mercury for atmosphere, is going to give us 0.937 atmospheres. All right, so that's good. Volume we have here in milliliters, but we're going to need it in liters. Well, a milliliter is just 1/1000th of a liter. So 1 liter is 1,000 milliliters. Milliliters will cancel, so 0.205 divided by 1,000 is going to be 0.205 liters. All right, so we got atmospheres, we got liters, mole, Kelvin. I think we're done. All right, so let me just scroll down just a little bit so we don't lose any of the information we have here. And we can fill in PV equals nRT. So pressure, 0.937 atmospheres. Volume, 205 liters. Okay. nRT, we're looking for T. And to get T by itself, we'll divide by N and R, both sides. So I'll just do that in this one step instead of taking 2 steps and writing all over the place. So N, we said, is 7.00 times 10 to the minus 3 moles. And finally, the gas constant, 0.0821 atmosphere, liter, mole, Kelvin. All right, so we have atmospheres on top, atmospheres on the bottom. We have liters on top, liters on the bottom. And we have moles here on top of the bottom and moles on the bottom of the bottom. And we have 1 over K, and that brings K out on top. So let me scroll down, give you a chance to calculate this in your calculators. And you're left with 334 point a quarter, somewhere around there, Kelvin. 3 sig figs, 3 sig figs, 3 sig figs, and the gas constant actually extends more, but we have 3 sig figs there. So we're just going to keep 3 sig figs in our answer. I'll just not even bother writing the 0.2352532 and all that junk. So this is going to be a temperature of 334 Kelvin. So hopefully you could see in the first one we had a case 1 and a case 2. Use the combined gas law. If you have just one case and you're not doing a before and after, use the ideal gas law.